Hello, my name is Fangshuo Liao. In this video, I'm presenting my work on the convergence of shallow neural network training with randomly masked neurons. This work is done with my PhD advisor, Anastasios Kyriadis at Rice University. To start, let's provide some background knowledge on using the neural tangent kernel to analyze the training convergence of neural networks. We consider a ReLU-activated one-hit layer MLP represented by the function f here. W's here is the first layer weights, and ARs here are the second layer weights. As in previous work, we assume that only the first layer weights are trainable, and denote its value in the case iteration as WK. In iteration k, we denote the output of the function for the ith input as UKI, and denote the output vector for all inputs as UK. Based on UK, we can define the MSE loss at iteration k as LK here. Y here is the vector of the labels. Assume we have n samples, the neural tangent kernel NTK in the case iteration can be represented as an n by n matrix, with the ij's entry being a function on the pairwise input vectors xi and xj's. Here, we can see that hkij depends on the weight in iteration k, wkrs. Using the first order Taylor expansion, we can see that the loss at iteration k plus 1 is just approximately the loss at iteration k minus the step size eta times the inner product term. The inner product term is essentially the norm of uk minus y induced by the matrix hk. Therefore, if hk is positive definite, we can guarantee that the loss decreases during the training. Indeed, this is true when the input data xi xj's are non-degenerate and the weight perturbation is small. However, the above analysis only applies to the gradient update scenario when all weight vectors are updated in each iteration based on a fixed neural network function. In this work, we consider a more general scenario. We start with a dense full network. In each global iteration k, we sample a set of masks from some distributions, each of these masks deactivating a subset of the hidden neurons. These masks then define a set of subnetworks. We then perform local training on these subnetworks using gradient descent and arrive at a set of the locally trained subnetworks. We compute the aggregation weights based on the masks and use this aggregation weights to combine all the locally trained subnetworks into the aggregated network. This aggregated network will become the initial dense network in the next global iteration. Mathematically, we can treat the mask in global iteration k as a matrix mk, with mkrl being the value in the rth row and the else column. mkrl is essentially a binary value representing whether neuron R is active in subnetwork L. We can write out the form of the subnetwork function by inserting mkrl in the summation here. We perform local training on these subnetwork functions using the MSE loss as well, and we will analyze the loss dynamic on the aggregated full network. We use tau to denote the number of local training steps, and p denotes the number of subnetworks. Moreover, we will use c to denote the probability that a neuron is active in a specific subnetwork, and theta as the probability that a neuron is active in at least one subnetwork. Based on different mask distributions, and as we will talk about later, we will have different values of x's and thetas. When xc is 1, meaning that every neuron is active in every subnetwork, and when there is only one subnetwork, we arrive at the regular gradient descent. But our framework also connects with other existing methods. For generic C, when the number of local training steps tau is 1 and the number of subnetworks p is 1, we get the dropout algorithm. When tau is 1 and p is greater than 1, we arrive at the multi-sample dropout. And when tau is greater than 1 and p is greater than 1, we have the multi-worker IST, the independent subnet training, which is a novel distributed training algorithm. To show the convergence guarantee of the framework above, we can no longer utilize the original NTK, since the mask introduces another randomness, meaning that even when the weights of the neural network are fixed, we can still get different outputs based on different masks. Therefore, what's central to our idea is the definition of the masked NTK, which includes the mask entries mkrls in the summation of the form of NTK. In our definition, we don't enforce the iteration index of the mask k prime to be equal to the index of the weights k, only due to mathematical convenience. Practically, we will only use the masked NTK when k prime equals to k. And we will show that the masked NTK has a nice concentration property around the ordinary infinite width NTK. Therefore, under the case of sufficient overparameterization and small weight perturbation, it stays positive definite throughout training. That is, the minimum eigenvalue of all of our masked NTK is greater than or equal to lambda 0/2, with lambda here being a strictly positive value. With the positive definiteness of the masked NTK, we can now show the linear convergence of the subnetwork training under several conditions. The first one here is that we need a large enough overparameterization, M, and a small enough step size eta. As n grows larger, we basically need a larger number of overparameterization and a smaller step size. The second condition is that the sum of the weight perturbation up to the global iteration k and the current loss plus some error term is bounded by a small number r. Under these two conditions, we can show that the subnetwork local training converges linearly. And also during the local training, the weight perturbation is also bounded. However, this result only shows that the subnetwork training behaves well. It does not guarantee that the subnetwork training guarantees the loss decrease on the whole network. For different mask distributions, we use different techniques to deal with this difficulty. Our first result is based on the Bernoulli mask, where each mask entry MKRL is sampled from a simple Bernoulli distribution with parameter C. Similar to the lemma for subnetwork training convergence, under the case of large enough M and small enough eta, we have that the loss decreases linearly to some error region B1, with B1 represented below. B1 here has three terms. When C is 1, meaning that a neuron is determined to be active in all of the subnetworks, then all three terms reduces to 0. When C is not 1, the last term grows as we have a larger tau and reduces to 0 when tau is 1. The second term decreases as we increase P, meaning that more subnetworks will be more helpful for the convergence. And the first term decreases as we increase M, meaning that more overparameterization is also better for the convergence. When the initialization scale kappa is 1 over the square root of n, B1 becomes a constant term. We can also overload this theorem with different values of taus and p's to get a convergence guarantee for our dropout, multi-sample dropout, as well as the multi-worker IST. Now, let's consider a different mask distribution, the categorical distribution. In this case, each neuron is distributed with uniform probability to one and only one subnetwork. Under this mask distribution, we have the convergence theorem in a similar form. Let gamma be the cubic root of 1 minus 1 over p. Then, under sufficiently large overparameterization M and small enough step size eta, we can show that the loss converges linearly to some error region. We notice here that gamma controls the speed of the loss decrease. Increase the number of subnetworks P will cause gamma to increase, thus results in a slower convergence. This means that more subnetworks under categorical mask is actually harmful for the convergence. To summarize, in our paper, we proposed a theoretical framework that generalizes both vanilla gradient descent and some other existing training algorithms based on the random neural masking. We defined the masked NTK and used it to analyze the local training convergence of the subnetworks. And we analyzed the whole network convergence under two different mask distributions. In our paper, we also included some experiments to validate our theory. And that's all for the presentation. And thanks for listening.